So here on a beautiful Friday afternoon, mid-afternoon, on the outskirts of Amsterdam at the University of Amsterdam Science Park with radio astronomer Joe Callingham, who's originally from somewhere near Brisbane in Australia, who has been working on the SKA International Radio Astronomy Project. But what is your title at ASTRON, Joe?
So my title at ASTRON, which is the Netherlands Institute for Radio Astronomy, is head of the Square Kilometre Array Science Group, and we're here in the University of Amsterdam, where I'm an associate professor as well.
And the SKA has been in the works for what, since the mid-90s. And the shocking thing is, it's only $1 billion project, and it ended up being two massive arrays, one based in Western Australia, one based in South Africa, due to come online, first light for 2027, full operation by 2029, correct?
That's correct, yeah. So we're very excited the project's becoming real. We're right in the middle of construction at the moment, and we can't wait to see the first science-ready images in just the next year or two.
And it's only €1 billion. I mean,
Only €1 billion.
That's pocket change.
Depends
for a
on your
lot of
definition,
people.
but yeah, it took us a long time to accumulate that money. It's just exciting to be able to spend it with this construction that's going on now.
And you told me three very interesting things, the three things that you mentioned that would not necessarily come off the top of your head or the top of one's head when thinking about such a project. But first of all, tell us why the SKA is unique in both of its frequency ranges, and then the three science things.
Sure.
The three science goals that you particularly think are interesting.
Sure. So the SKA is going to revolutionize our understanding of the universe, largely because it's going to have a sensitivity and the resolution that's unparalleled by any other radio telescope that we've ever built. And what I particularly find incredibly exciting about the Square Kilometre Array project is I think it will find the first aurora on other planets outside of our solar system. So you might have familiarity of the Northern Lights and seeing that. If I could turn your eyes into radio receivers, that would be even brighter. It would actually just saturate your vision. And so we're hunting for that on other planets, around other stars, and that's what I think one of the amazing goals of the SKA will produce in the next 5 to 10 years is the first detection of exoplanet at radio frequencies. And that will tell us all about the magnetic field. The other one,
but let's stay on that for a minute. Now,
Sure.
why? And you mentioned this is important because we're able to detect, or we're going to be able to detect more and more Earth mass planets in the so-called habitable zone, defined as where an Earth a terrestrial mass planet can harbor liquid water at its surface. But as I've previously written in Forbes, just because you can harbor liquid water at the surface doesn't mean you have life. You also need a lot of other things, and one is a geomagnetic field, correct?
Correct, yeah. So the idea here is that trying to find whether a planet is habitable, like we have on Earth, has many different pieces of that puzzle. And one really important piece we think is the magnetic field of Earth. That you can imagine it like a shield. It protects us from solar activity. So you have these big coronal mass ejections from the sun, and our magnetic field deflects those and makes sure it doesn't strip our atmosphere. If you compare us to Mars, Mars doesn't have that. And over millions of years, this activity slowly stripped the atmosphere. And so the idea is that we think to find an Earth-like planet, not only do you need to find it in the habitable zone, you have to find it with a magnetic field. And that's because you want to make sure it has an atmosphere, it has liquid water on the surface. And so that's one hope.
And to date, has anybody spotted a aurora on an exoplanet?
No, this is what my team are working on right now with the LOFAR radio telescope, which is run by the Netherlands. We're trying really hard, but we really need that extra sensitivity, and the SKA will provide that.
And then what's the next? You mentioned the second.
The second most exciting thing I think the SKA will begin to solve is tests of general relativity, Einstein's theory of general relativity in really extreme physics scenarios. So you have neutron stars, which is the end life of some of the most massive stars in the universe, and they can form in binary pairs. And what you can do is use their motion to test exactly how Einstein's theory predicts their motion. And now with the SKA, because we have such good resolution and sensitivity, we can really push that theory even more and more to a breaking point and maybe find new physics. That's the hope, at least.
And then the third thing.
And the third thing is we don't understand how galaxies evolve and change over time. So we're part of this Milky Way. This is our home, but how did it come to be? And how has that changed over time? And the SKA can peer back further and further and further than any other radio telescope, and we can begin to understand how we assembled and how we came to produce the galaxy we live in today.
And then you mentioned that the Netherlands is unique. You're kind of the radio astronomy community here are kind of the kings of radio astronomy because you've been doing it for so long. Explain what you mean by that.
So radio astronomy in the Netherlands has a very, very long tradition dating back to Oort and the end of World War II.
Jan Oort, right?
Jan Oort, yeah. So Professor Jan Oort based at Leiden. And we've capitalize on that expertise, both theoretical and engineering, to really provide some of the understanding for the square kilometre array. Without the algorithms we've developed here and the engineering skills we've built over time in the Netherlands, the SKA wouldn't be possible. And so that's what we really hope to contribute to the project as well, is that high level expertise to make sure the project is a success.
But AI is helping you in some ways, but you say it's not really going to help you with the data analysis in the way that one might think.
Yeah, so one of the big problems with a square kilometre array, or the challenges maybe the way I should phrase it, is trying to deal with the data rate. So this is going to produce such a high level of data, petabytes and petabytes a week of data. How do you process it and where do you store it? AI is probably not going to solve that problem for us. It might help us analyzing the data, we're looking for patterns, all that kind of stuff, but it's really not going to help us in terms of the hard problems of like how do we compute, do the computations, and where do we put this data after we do the computations so we can start doing science.
And then a year after the data is analyzed, initially for the first year it will be proprietary for the countries in the SKA, but then you say it's going to become available to the general astronomical public.
The exact time frame is not clear yet because the project's still in its early phases, but there will be a proprietary period. But just like any good astronomy project, after that point, anyone can have access to that data to do the best science they can.
And tell us also, you say, people, it's counterintuitive. Radio astronomy, it seems kind of foreign to most people. They can understand looking through an optical visual telescope or even an infrared telescope.
Yeah.
But this telescope is going to provide high resolution images.
Yes.
Literal images.
Yeah, so a lot of people think of a radio, they often think when they get in the car, they listen to radio. But just radio carries information in a lot of different forms, and one way is you can image it. And so that's where a lot of the computational skill comes in, is trying to turn those radio waves into an image. And that's what we want to do, because then you can image a galaxy, or you can find aurora on a planet, and you need to be able to make those images.
And then how long do you expect the SKA, when they're in full operation, to be taking data?
I imagine it's going to be such a large facility. I imagine it'll run for 50 years or more.
50 years or more.
Yeah.
Incredible.
Yeah.
And then the far future. You mentioned perhaps compatibility with existing radio telescopes on Earth. There would be some overlap with existing facilities. Could you talk about that a bit?
Yeah, so big win in radio astronomy is that you can kind of join together many different other radio telescopes. And so one of the goals in the long run with SKA is not only have you got a fantastic facility now, you could connect it to other radio telescopes to do, say, what's called very long baseline interferometry. So you get even higher resolution as well. So you could join to European radio telescopes, Chinese telescopes, Australian telescopes, American telescopes, and that could make some of the highest resolution images we've made with radio telescopes.
So Joe, thank you so much for your time today. I appreciate your generosity with your time. It was
a lot of fun. Thank you.
Rearranging your schedule, and we look forward to hearing more from you in the future.
Great. All right. Thank you very much.